This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition by Charles Darwin. Chapter number 4. Natural Selection, or the Survival of the Fittest. Section 1 of 3. Contents of this chapter include natural selection, its power compared with man's selection, its power on characters of trifling importance, its power at all ages and on both sexes, sexual selection, on the generality of intercrosses between the individuals of the same species, circumstances favourable and unfavourable to the results of natural selection, namely, intercrossing, isolation, number of individuals, slow action, extinction caused by natural selection, diversity of character related to the diversity of inhabitants of any small area and to naturalization, action of natural selection through divergence of character and extinction on the descendants from a common parent, explains the grouping of all organic beings, advance in organization, low forms preserved, convergence of character, indefinite multiplication of species, and summary. How will the struggle for existence, briefly discussed in the last chapter, act in regard to variation? Can the principle of selection, which we have seen is so potent in the hands of man, apply under nature? I think we shall see that it can act most efficiently. Let the endless number of slight variations and individual differences occurring in our domestic productions, and in a lesser degree in those under nature, be borne in mind, as well as the strength of the hereditary tendency. Under domestication, it may truly be said that the whole organization becomes in some degree plastic. But the variability which we almost universally meet with in our domestic productions is not directly produced, as Hooker and Asa Gray have well remarked, by man. He can neither originate varieties nor prevent their occurrence. He can only preserve and accumulate such as do occur. Unintentionally, he exposes organic beings to new and changing conditions of life, and variability ensues. But similar changes of conditions might and do occur under nature. Let it also be borne in mind how infinitely complex and close-fitting are the mutual relations of all organic beings to each other and to their physical conditions of life, and consequently what infinitely varied diversities of structure might be of use to each being under changing conditions of life. Can it then be thought improbable, seeing that variations useful to man have undoubtedly occurred, that other variations useful in some way to each being in the great and complex battle of life should occur in the course of many successive generations? If such do occur, can we doubt, remembering that many more individuals are born than can possibly survive, that individuals having any advantage, however slight, over others, would have the best chance of surviving and procreating their kind? On the other hand, we may feel sure that any variation in the least degree injurious would be rigidly destroyed. This preservation of favourable individual differences and variations, and the destruction of those which are injurious, I have called natural selection, or the survival of the fittest. Variations neither useful nor injurious would not be affected by natural selection, and would be left either a fluctuating element, as perhaps we see in certain polymorphic species, or would ultimately become fixed, owing to the nature of the organism and the nature of the conditions. Several writers have misapprehended or objected to the term natural selection. Some have even imagined that natural selection induces variability, whereas it implies only the preservation of such variations as arise and are beneficial to the being under its conditions of life. No one objects to agriculturists speaking of the potent effects of man's selection, and in this case the individual differences given by nature, which man for some objects selects, must of necessity first occur. Others have objected that the term selection implies conscious choice in the animals which become modified, and it has even been urged that, as plants have no volition, natural selection is not applicable to them. In the literal sense of the word, no doubt, natural selection is a false term, but whoever objected to chemists speaking of the elective affinities of the various elements? And yet an acid cannot strictly be said to elect the base with which it in preference combines. It has been said that I speak of natural selection as an active power or deity, but who objects to an author speaking of the attraction of gravity as ruling the movements of the planets? Everyone knows what is meant and is implied by such metaphorical expressions, and they are almost necessary for brevity. So again, it is difficult to avoid personifying the word nature, and I mean by nature only the aggregate action and product of many natural laws, and by laws the sequence of events as ascertained by us. With a little familiarity, such superficial objections will be forgotten. We shall best understand the probable course of natural selection by taking the case of a country undergoing some slight physical change, for instance of climate. The proportional numbers of its inhabitants will almost immediately undergo a change, and some species will probably become extinct. We may conclude, from what we have seen of the intimate and complex manner in which the inhabitants of each country are bound together, that any change in the numerical proportions of the inhabitants, independently of the change of climate itself, would seriously affect the others. If the country were open on its borders, new forms would certainly immigrate, and this would likewise seriously disturb the relations of some of the former inhabitants. Let it be remembered how powerful the influence of a single introduced tree or mammal has been shown to be. But in the case of an island, or of a country partly surrounded by barriers, into which new and better adapted forms could not freely enter, we should then have places in the economy of nature which would assuredly be better filled up if some of the original inhabitants were in some manner modified. For had the area been open to immigration, these same places would have been seized on by intruders. In such cases, slight modifications which in any way favoured the individuals of any species, by better adapting them to their altered conditions, would tend to be preserved, and natural selection would have free scope for the work of improvement. We have good reason to believe, as shown in the first chapter, that changes in the conditions of life give a tendency to increased variability, and in the foregoing cases the conditions changed, and this would manifestly be favourable to natural selection, by affording a better chance of the occurrence of profitable variations. Unless such occur, natural selection can do nothing. Under the term of variations, it must never be forgotten that mere individual differences are included. As man can produce a great result with his domestic animals and plants by adding up in any given direction individual differences, so could natural selection, but far more easily from having incomparably longer time for action. Nor do I believe that any great physical change, as of climate, or any unusual degree of isolation to check immigration, is necessary in order that new and unoccupied places should be left for natural selection to fill up by improving some of the varying inhabitants. For as all the inhabitants of each country are struggling together with nicely balanced forces, extremely slight modifications in the structure or habits of one species would often give it an advantage over others, and still further modifications of the same kind would often still further increase the advantage, as long as the species continued under the same conditions of life and profited by similar means of subsistence and defence. No country can be named in which all the native inhabitants are now so perfectly adapted to each other and to the physical conditions under which they live, that none of them could be still better adapted or improved. For in all countries the natives have been so far conquered by naturalised productions that they have allowed some foreigners to take firm possession of the land. And as foreigners have thus in every country beaten some of the natives, we may safely conclude that the natives might have been modified with advantage, so as to have better resisted the intruders. As man can produce, and certainly has produced, a great result by his methodical and unconscious means of selection, what may not natural selection effect? Man can act only on external and visible characters. Nature, if I may be allowed to personify the natural preservation or survival of the fittest, cares nothing for appearances, except in so far as they are useful to any being. She can act on every internal organ, on every shade of constitutional difference, on the whole machinery of life. Man selects only for his own good, nature only for that of the being which she tends. Every selected character is fully exercised by her, as is implied by the fact of their selection. Man keeps the natives of many climates in the same country. He seldom exercises each selected character in some peculiar and fitting manner. He feeds a long and a short-beaked pigeon on the same food. He does not exercise a long-backed or long-legged quadruped in any particular manner. He exposes sheep with long and short wool to the same climate, does not allow the most vigorous males to struggle for the females. He does not rigidly destroy all inferior animals, but protects during each varying season, as far as lies in his power, all his productions. He often begins his selection by some half-monstrous form, or at least by some modification prominent enough to catch the eye, or to be plainly useful to him. Under nature, the slightest differences of structure or constitution may well turn the nicely balanced scale in the struggle for life, and so be preserved. How fleeting are the wishes and efforts of man! How short his time, and consequently how poor will be his results, compared with those accumulated by nature during whole geological periods! Can we wonder then that nature's productions should be far truer in character than man's productions, that they should be infinitely better adapted to the most complex conditions of life, and should plainly bear the stamp of far higher workmanship? It may metaphorically be stated that natural selection is daily and hourly scrutinizing throughout the world the slightest variations, rejecting those that are bad, preserving and adding up all that are good, silently and insensibly working, whenever and wherever opportunity offers, at the improvement of each organic being in relation to its organic and inorganic conditions of life. We see nothing of these slow changes in progress, until the hand of time has marked the long lapse of ages, and then so imperfect is our view into long past geological ages, that we see only that the forms of life are now different from what they formerly were. In order that any great amount of modification should be effected in a species, a variety, when once formed, must again, perhaps after a long interval of time, vary, or present individual differences of the same favourable nature as before, and these must again be preserved, and so onward, step by step. Seeing that individual differences of the same kind perpetually recur, this can hardly be considered as an unwarrantable assumption. But whether it is true, we can judge only by seeing how far the hypothesis occurs with and explains the general phenomena of nature. On the other hand, the ordinary belief that the amount of possible variation is a strictly limited quantity is likewise a simple assumption. Although natural selection can act only through and for the good of each being, yet characters and structures, which we are apt to consider as of very trifling importance, may thus be acted on. When we see leaf-eating insects green, and bark-feeders mottled grey, the alpine ptarmigan white in winter, the red grouse the colour of heather, we must believe that these tints are of service to these birds and insects in preserving them from danger. Grouse, if not destroyed at some period of their lives, would increase in countless numbers. They are known to suffer largely from birds of prey, and hawks are guided by eyesight to their prey. So much so, that on parts of the continent persons are warned not to keep white pigeons, as being the most liable to destruction. Hence natural selection might be effective in giving the proper colour to each kind of grouse, and in keeping that colour, when once required, true and constant. Nor ought we to think that the occasional destruction of an animal of any particular colour would produce little effect. We should remember how essential it is, in a flock of white sheep, to destroy a lamb with the faintest trace of black. We have seen how the colour of hogs, which feed on the paint root in Virginia, determines whether they shall live or die. In plants, the down on the fruit and the colour of the flesh are considered by botanists as characters of the most trifling importance. Yet we hear from an excellent horticulturist, Downing, that in the United States, smooth-skinned fruits suffer far more from a beetle, a curculio, than those with down, that purple plums suffer far more from a certain disease than yellow plums, whereas another disease attacks yellow-fleshed peaches far more than those with other coloured flesh. If, with all the aids of art, these slight differences make a great difference in cultivating the several varieties, assuredly in a state of nature, where the trees would have to struggle with other trees and with a host of enemies, such differences would effectually settle which variety, whether a smooth or downy, a yellow or a purple-fleshed fruit, should succeed. In looking at many small points of difference between species, which, as far as our ignorance permits us to judge, seem quite unimportant, we must not forget that climate, food, etc., have no doubt produced some direct effect. It is also necessary to bear in mind that, owing to the law of correlation, when one part varies and the variations are accumulated through natural selection, other modifications, often of the most unexpected nature, will ensue. As we see that those variations which, under domestication, appear at any particular period of life, tend to reappear in the offspring at the same period, for instance, in the shape, size and flavour of the seeds of the many varieties of our culinary and agricultural plants, in the caterpillar and cocoon stages of the varieties of the silkworm, in the eggs of poultry and in the colour of the down of their chickens, in the horns of our sheep and cattle when nearly adult. So, in a state of nature, natural selection will be enabled to act on and modify organic beings at any age, by the accumulation of variations profitable at that age, and by their inheritance at a corresponding age. If it profit a plant to have its seeds more and more widely disseminated by the wind, I can see no greater difficulty in this being effected through natural selection than in the cotton planter increasing and improving by selection the down in the pods on his cotton trees. Natural selection may modify and adapt the larva of an insect to a score of contingencies, wholly different from those which concern the mature insect. And these modifications may affect, through correlation, the structure of the adult. So, conversely, modifications in the adult may affect the structure of the larva. But in all cases, natural selection will ensure that they shall not be injurious, for if they were so, the species would become extinct. Natural selection will modify the structure of the young in relation to the parent, and of the parent in relation to the young. In social animals, it will adapt the structure of each individual for the benefit of the whole community, if the community profits by the selected change. What natural selection cannot do is to modify the structure of one species without giving it any advantage for the good of another species, and though statements to this effect may be found in works of natural history, I cannot find one case which will bear investigation. A structure used only once in an animal's life, if of high importance to it, might be modified to any extent by natural selection. For instance, the great jaws possessed by certain insects, used exclusively for opening the cocoon, or the hard tip to the beak of unhatched birds, used for breaking the eggs. It has been asserted that of the best short-beaked tumbler pigeons, a greater number perish in the egg than are able to get out of it, so that fanciers assist in the act of hatching. Now, if nature had to make the beak of a full-grown pigeon very short for the bird's own advantage, the process of modification would be very slow, and there would be simultaneously the most rigorous selection of all the young birds within the egg which had the most powerful and hardest beaks. For all with weak beaks would inevitably perish, or more delicate and more easily broken shells might be selected, the thickness of the shell being known to vary like every other structure. It may be well here to remark that with all beings there must be much fortuitous destruction, which can have little or no influence on the course of natural selection. For instance, a vast number of eggs or seeds are annually devoured, and these could be modified through natural selection only if they varied in some manner which protected them from their enemies. Yet many of these eggs or seeds would perhaps, if not destroyed, have yielded individuals better adapted to their conditions of life than any of those which happened to survive. So again, a vast number of mature animals and plants, whether or not they be the best adapted to their conditions, must be annually destroyed by accidental causes, which would not be in the least degree mitigated by certain changes of structure or constitution, which would in other ways be beneficial to the species. But let the destruction of the adults be ever so heavy, if the number which can exist in any district be not wholly kept down by such causes, or again, let the destruction of eggs or seeds be so great that only 100th or 1,000th part are developed, yet of those which do survive, the best adapted individuals, supposing that there is any variability in a favourable direction, will tend to propagate their kind in larger numbers than the less well adapted. If the numbers be wholly kept down by the causes just indicated, as will often have been the case, natural selection will be powerless in certain beneficial directions. But this is no valid objection to its efficiency at other times and in other ways, for we are far from having any reason to suppose that many species ever undergo modification and improvement at the same time in the same area. Sexual selection. Inasmuch as peculiarities often appear under domestication in one sex, and become hereditarily attached to that sex, so no doubt it will be under nature. Thus it is rendered possible for the two sexes to be modified through natural selection in relation to different habits of life, as is sometimes the case, or for one sex to be modified in relation to the other sex, as commonly occurs. This leads me to say a few words on what I have called sexual selection. This form of selection depends not on a struggle for existence in relation to other organic beings or to external conditions, but on a struggle between the individuals of one sex, generally the males, for the possession of the other sex. The result is not death to the unsuccessful competitor, but few or no offspring. Sexual selection is therefore less rigorous than natural selection. Generally, the most vigorous males, those which are best fitted for their places in nature, will leave most progeny. But in many cases, victory depends not so much on general vigour, but on having special weapons confined to the male sex. A hornless stag or spurless cock would have a poor chance of leaving numerous offspring. Sexual selection, by always allowing the victor to breed, might surely give indomitable courage, length of spur, and strength to the wing to strike in the spurred leg. in nearly the same manner as does the brutal cockfighter by the careful selection of his best cocks. How low in the scale of nature the law of battle descends, I know not. Male alligators have been described as fighting, bellowing and whirling around, like Indians in a war dance, for the possession of the females. Male salmons have been observed fighting all day long. Male stag beetles sometimes bear wounds from the huge mandibles of other males. The males of certain hymenopterous insects have been frequently seen by that inimitable observer, M. Fabre, fighting for a particular female, who sits by, an apparently unconcerned beholder of the struggle, and then retires with the conqueror. The war is, perhaps, severest between the males of polygamous animals, and these seem oftenest provided with special weapons. The males of carnivorous animals are already well armed, though to them and to others special means of defence may be given through means of sexual selection, as the mane of the lion and the hooked jaw to the male salmon, for the shield may be as important for victory as the sword or spear. Among birds the contest is often of a more peaceful character. All those who have attended to the subject believe that there is the severest rivalry between the males of many species to attract by singing the females. The rock thrush of Guyana, birds of paradise, and some others congregate, and successive males display with the most elaborate care, and show off in the best manner, their gorgeous plumage. They likewise perform strange antics before the females, which, standing by as spectators, at last choose the most attractive partner. Those who have closely attended to birds in confinement will know that they often take individual preferences and dislikes. Thus Sir R. Heron has described how a pied peacock was eminently attractive to all his hen birds. I cannot here enter on the necessary details, but if man can in a short time give beauty and an elegant carriage to his bantams, according to his standard of beauty, I can see no good reason to doubt that female birds, by selecting, during thousands of generations, the most melodious or beautiful males, according to their standard of beauty, might produce a marked effect. Some well-known laws, with respect to the plumage of male and female birds, in comparison with the plumage of the young, can partly be explained through the action of sexual selection on variations occurring at different ages, and transmitted to the males alone, or to both sexes at corresponding ages, but I have not space here to enter on this subject. Thus it is, as I believe, that when the males and females of any animal have the same general habits of life, but differ in structure, colour, or ornament, such differences have been mainly caused by sexual selection, that is, by individual males having had, in successive generations, some slight advantage over other males, in their weapons, means of defence, or charms, which they have transmitted to their male offspring alone. Yet I would not wish to attribute all sexual differences to this agency, for we see in our domestic animals peculiarities arising and becoming attached to the male sex, which apparently have not been augmented through selection by man. The tuft of hair on the breast of the wild turkey cock cannot be of any use, and it is doubtful whether it can be ornamental in the eyes of the female bird. Indeed, had the tuft appeared under domestication, it would have been called a monstrosity. Illustrations of the action of natural selection, or the survival of the fittest. In order to make it clear how, as I believe, natural selection acts, I must beg permission to give one or two imaginary illustrations. Let us take the case of a wolf, which preys on various animals, securing some by craft, some by strength, and some by fleetness. And let us suppose that the fleetest prey, a deer for instance, had from any change in the country increased in numbers, or that other prey had decreased in numbers during that season of the year when the wolf was hardest pressed for food. Under such circumstances, the swiftest and slimmest wolves have the best chance of surviving, and so be preserved or selected, provided always that they retained strength to master their prey at this or some other period of the year when they were compelled to prey on other animals. I can see no more reason to doubt that this would be the result than that man should be able to improve the fleetness of his greyhounds by careful and methodical selection, or by that kind of unconscious selection which follows from each man trying to keep the best dogs, without any thought of modifying the breed. I may add that, according to Mr. Pearce, there are 2 varieties of the wolf inhabiting the Catskill Mountains in the United States, one with a light greyhound-like form which pursues deer, and the other more bulky, with shorter legs, which more frequently attacks the shepherd's flocks. Even without any change in the proportional numbers of the animals on which our wolf preyed, a cub might be born with an innate tendency to pursue certain kinds of prey. Nor can this be thought very improbable, for we often observe great differences in the natural tendencies of our domestic animals, one cat, for instance, taking to catching rats, another mice; one cat, according to Mr. St. John, bringing home winged game, another hares or rabbits, and another hunting on marshy ground, and almost nightly catching woodcocks or snipes. The tendency to catch rats rather than mice is known to be inherited. Now, if any slight innate change of habit or of structure benefited an individual wolf, it would have the best chance of surviving and of leaving offspring. Some of its young would probably inherit the same habits or structure, and by the repetition of this process, a new variety might be formed, which would either supplant or coexist with the parent form of wolf. Or, again, the wolves inhabiting a mountainous district and those frequenting the lowlands would naturally be forced to hunt different prey, and from the continued preservation of the individuals best fitted for the 2 sites, 2 varieties might slowly be formed. These varieties would cross and blend where they met, but to this subject of intercrossing we shall soon have to return. It should be observed that in the above illustration I speak of the slimmest individual wolves, and not of any single strongly marked variation having been preserved. In former editions of this work I sometimes spoke as if this latter alternative had frequently occurred. I saw the great importance of individual differences, and this led me fully to discuss the results of unconscious selection by man, which depends on the preservation of all the more or less valuable individuals, and on the destruction of the worst. I saw also that the preservation in a state of nature of any occasional deviation of structure, such as a monstrosity, would be a rare event, and that, if at first preserved, it would generally be lost by subsequent intercrossing with ordinary individuals. Nevertheless, until reading an able and valuable article in the North British Review, 1867, I did not appreciate how rarely single variations, whether slight or strongly marked, could be perpetuated. The author takes the case of a pair of animals producing during their lifetime 200 offspring, of which, from various causes of destruction, only 2 on an average survive to procreate their kind. This is rather an extreme estimate for most of the higher animals, but by no means so for many of the lower organisms. He then shows that if a single individual were born which varied in some manner, giving it twice as good a chance of life as that of the other individuals, yet the chances would be strongly against its survival. Supposing it to survive and to breed, and that half its young inherited the favourable variation, still, as the reviewer goes on to show, the young would have only a slightly better chance of surviving and breeding, and this chance would go on decreasing in the succeeding generations. The justice of these remarks cannot, I think, be disputed. If, for instance, a bird of some kind could procure its food more easily by having its beak curved, and if one were born with its beak strongly curved, and which consequently flourished, nevertheless there would be a very poor chance of this one individual perpetuating its kind to the exclusion of the common form. But there can hardly be a doubt, judging by what we see taking place under domestication, that this result would follow from the preservation during many generations of a large number of individuals with more or less strongly curved beaks, and from the destruction of a still larger number with the straightest beaks. It should not, however, be overlooked that certain rather strongly marked variations, which no one would rank as mere individual differences, frequently recur owing to a similar organisation being similarly acted on, of which fact numerous instances could be given with our domestic productions. In such cases, if the varying individual did not actually transmit to its offspring its newly acquired character, it would undoubtedly transmit to them, as long as the existing conditions remained the same, a still stronger tendency to vary in the same manner. There can also be little doubt that the tendency to vary in the same manner has often been so strong that all the individuals of the same species have been similarly modified without the aid of any form of selection, or only a third, fifth, or 10th part of the individuals may have been thus affected, of which fact several instances could be given. Thus Graber estimates that about 1/5 of the guillemots in the Faroe Islands consist of a variety so well marked that it was formerly ranked as a distinct species under the name of Urea lacrymans. In cases of this kind, if the variation were of a beneficial nature, the original form would soon be supplanted by the modified form through the survival of the fittest. To the effects of intercrossing in eliminating variations of all kinds I shall have to recur, but it may be here remarked that most animals and plants keep to their proper homes, and do not needlessly wander about. We see this even with migratory birds, which almost always return to the same spot. Consequently, each newly formed variety would generally be at first local, as seems to be the common rule with varieties in a state of nature, so that similarly modified individuals would soon exist in a small body together, and would often breed together. If the new variety were successful in its battle for life, it would slowly spread from a central district, competing with and conquering the unchanged individuals on the margins of an ever-increasing circle. It may be worth while to give another and more complex illustration of the action of natural selection. Certain plants excrete sweet juice, apparently for the sake of eliminating something injurious from the sap. This is effected, for instance, by glands at the base of the stipules in some leguminosæ and at the backs of the leaves of the common laurel. This juice, though small in quantity, is greedily sought by insects, but their visits do not in any way benefit the plant. Now, let us assume that the juice or nectar was excreted from the inside of the flowers of a certain number of plants of any species. Insects, in seeking the nectar, would get dusted with pollen, and would often transport it from one flower to another. The flowers of two distinct individuals of the same species would thus get crossed, and the act of crossing, as can be fully proved, gives rise to vigorous seedlings, which consequently would have the best chance of flourishing and surviving. The plants which produced flowers with the largest glands or nectaries, excreting most nectar, would oftenest be visited by insects, and would oftenest be crossed, and so, in the long run, would gain the upper hand and form a local variety. The flowers also, which had their stamens and pistils placed in relation to the size and habits of the particular insect which visited them, so as to favour in any degree the transportal of the pollen, would likewise be favoured. We might have taken the case of insects visiting flowers for the sake of collecting pollen instead of nectar, and as pollen is formed for the sole purpose of fertilisation, its destruction appears to be a simple loss to the plant. Yet if a little pollen were carried, at first occasionally and then habitually, by the pollen-devouring insects from flower to flower, and a cross thus effected, although 9/10 of the pollen were destroyed, it might still be a great gain to the plant to be thus robbed, and the individuals which produced more and more pollen and had larger anthers would be selected. When our plant, by the above process long continued, had been rendered highly attractive to insects, they would, unintentionally on their part, regularly carry pollen from flower to flower, and that they do this effectually I could easily show by many striking facts. I will give only one, as likewise illustrating one step in the separation of the sexes of plants. Some holly trees bear only male flowers, which have 4 stamens, producing a rather small quantity of pollen, and a rudimentary pistil. Other holly trees bear only female flowers. These have a full-sized pistil, and 4 stamens with shrivelled anthers, in which not a grain of pollen can be detected. Having found a female tree exactly 60 yards from a male tree, I put the stigmas of 20 flowers, taken from different branches, under the microscope, and on all, without exception, there were a few pollen grains, and on some a profusion. As the wind had set for several days from the female to the male tree, the pollen could not thus have been carried. The weather had been cold and boisterous, and therefore not favourable to bees. Nevertheless, every female flower which I examined had been effectually fertilised by the bees, which had flown from tree to tree in search of nectar. But to return to our imaginary case, as soon as the plant had been rendered so highly attractive to insects that pollen was regularly carried from flower to flower, another process might commence. No naturalist doubts the advantage of what has been called the physiological division of labour. Hence we may believe that it would be advantageous to a plant to produce stamens alone in one flower, or on one whole plant, and pistils alone in another flower or on another plant. In plants under culture and placed under new conditions of life, sometimes the male organs and sometimes the female organs become more or less impotent. Now, if we suppose this to occur in ever so slight a degree under nature, then, as pollen is already carried regularly from flower to flower, and as a more complete separation of the sexes of our plant would be advantageous, on the principle of the division of labour, individuals with this tendency more and more increased would be continually favoured or selected, until at last a complete separation of the sexes might be effected. It would take up too much space to show the various steps, through dimorphism and other means, by which the separation of the sexes in plants of various kinds is apparently now in progress, but I may add that some of the species of holly in North America are, according to Asa Gray, in an exactly intermediate condition, or, as he expresses it, are more or less dioeciously polygamous. Let us now turn to the nectar-feeding insects. We may suppose the plant of which we have been slowly increasing the nectar by continued selection to be a common plant, and that certain insects depended in part on its nectar for food. I could give many facts showing how anxious bees are to save time. For instance, their habit of cutting holes and sucking the nectar at the bases of certain flowers, which with a very little more trouble they can enter by the mouth. Bearing such facts in mind, it may be believed that under certain circumstances individual differences in the curvature or length of the proboscis, etc., too slight to be appreciated by us, might benefit a bee or other insect, so that certain individuals would be able to obtain their food more quickly than others, and thus the communities to which they belonged would flourish and throw off many swarms inheriting the same peculiarities. The tubes of the corolla of the common red or incarnate clovers, Trifolium pratense and incarnatum, do not on a hasty glance appear to differ in length, yet the hive bee can easily suck the nectar out of the incarnate clover, but not out of the common red clover, which is visited by humble bees alone, so that whole fields of the red clover offer in vain an abundant supply of precious nectar to the hive bee. That this nectar is much liked by the hive bee is certain, for I have repeatedly seen, but only in the autumn, many hive bees sucking the flowers through holes bitten in the base of the tube by humble bees. The difference in the length of the corolla in the two kinds of clover, which determines the visits of the hive bee, must be very trifling, for I have been assured that when red clover has been mown, the flowers of the second crop are somewhat smaller, and that these are visited by many hive bees. I do not know whether this statement is accurate, nor whether another published statement can be trusted, namely, that the Ligurian bee, which is generally considered a mere variety of the common hive bee, and which freely crosses with it, is able to reach and suck the nectar of the red clover. Thus, in a country where this kind of clover abounded, it might be a great advantage to the hive bee to have a slightly longer or differently constructed proboscis. On the other hand, as the fertility of this clover absolutely depends on bees visiting the flowers, if humble bees were to become rare in any country, it might be a great advantage to the plant to have a shorter or more deeply divided corolla, so that the hive bees should be enabled to suck its flowers. Thus I can understand how a flower and a bee might slowly become, either simultaneously or one after the other, modified and adapted to each other in the most perfect manner, by the continued preservation of all the individuals which presented slight deviations of structure mutually favourable to each other. I am well aware that this doctrine of natural selection, exemplified in the above imaginary instances, is open to the same objections which were first urged against Sir Charles Lyell's noble views on the modern changes of the earth, as illustrative of geology, but we now seldom hear the agencies which we still see at work spoken of as trifling and insignificant, when used in explaining the excavation of the deepest valleys, or the formation of long lines of inland cliffs. Natural selection acts only by the preservation and accumulation of small inherited modifications, each profitable to the preserved being, and as modern geology has almost banished such views as the excavation of a great valley by a single diluvial wave, so will natural selection banish the belief of the continued creation of new organic beings, or of any great and sudden modification in their structure. End of section 1 of chapter 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The origin of species by means of natural selection, or the preservation of favoured races in the struggle for life. 6th London edition by Charles Darwin. Chapter number 4. Natural selection, or the survival of the fittest. Section 2 of 3. On the intercrossing of individuals. I must here introduce a short digression. In the case of animals and plants with separated sexes, it is of course obvious that two individuals must always, with the exception of the curious and not well understood cases of parthenogenesis, unite for each birth. But in the case of hermaphrodites, this is far from obvious. Nevertheless, there is reason to believe that with all hermaphrodites, two individuals, either occasionally or habitually, concur for the reproduction of their kind. This view was long ago doubtfully suggested by Sprengel, Knight, and Kölreuter. We shall presently see its importance, but I must here treat the subject with extreme brevity, though I have the materials prepared for an ample discussion. All vertebrate animals, all insects, and some other large groups of animals, pair for each birth. Modern research has much diminished the number of supposed hermaphrodites, and of real hermaphrodites a large number pair. That is, two individuals regularly unite for reproduction, which is all that concerns us. But still there are many hermaphrodite animals which certainly do not habitually pair, and a vast majority of plants are hermaphrodites. What reason, it may be asked, is there for supposing in these cases that two individuals ever concur in reproduction? As it is impossible here to enter on details, I must trust to some general considerations alone. In the first place, I have collected so large a body of facts, and made so many experiments, showing, in accordance with the almost universal belief of breeders, that with animals and plants, a cross between different varieties, or between individuals of the same variety but of another strain, gives vigour and fertility to the offspring, and on the other hand, that close interbreeding diminishes vigour and fertility. that these facts alone incline me to believe that it is a general law of nature that no organic being fertilizes itself for a perpetuity of generations, but that a cross with another individual is occasionally, perhaps at long intervals of time, indispensable. On the belief that this is a law of nature, we can, I think, understand several large classes of facts, such as the following, which on any other view are inexplicable. Every hybridizer knows how unfavourable exposure to wet is to the fertilization of a flower. Yet what a multitude of flowers have their anthers and stigmas fully exposed to the weather. If an occasional cross be indispensable, notwithstanding that the plant's own anthers and pistil stand so near each other as almost to ensure self-fertilization, the fullest freedom for the entrance of pollen from another individual will explain the above state of exposure of the organs. Many flowers, on the other hand, have their organs of fructification closely enclosed, as in the great Papilionaceous or pea family, but these almost invariably present beautiful and curious adaptations in relation to the visits of insects. So necessary are the visits of bees to many papilionaceous flowers, that their fertility is greatly diminished if these visits be prevented. Now it is scarcely possible for insects to fly from flower to flower, and not to carry pollen from one to the other, to the great good of the plant. Insects act like a camel hair pencil, and it is sufficient to ensure fertilization just to touch with the same brush the anthers of one flower and then the stigma of another. But it must not be supposed that bees would thus produce a multitude of hybrids between distinct species. For if a plant's own pollen and that from another species are placed on the same stigma, the former is so prepotent that it invariably and completely destroys, as has been shown by Gärtner, the influence of the foreign pollen. When the stamens of a flower suddenly spring towards the pistil, or slowly move one after the other towards it, the contrivance seems adapted solely to ensure self-fertilization, and no doubt it is useful for this end. But the agency of insects is often required to cause the stamens to spring forward, as Kölreuter has shown to be the case with the barberry. And in this very genus, which seems to have a special contrivance for self-fertilization, it is well known that, if closely allied forms or varieties are planted near each other, it is hardly possible to raise pure seedlings, so largely do they naturally cross. In numerous other cases, far from self-fertilization being favoured, there are special contrivances which effectually prevent the stigma receiving pollen from its own flower, as I could show from the works of Sprengel and others, as well as from my own observations. For instance, in Lobelia fulgens there is a really beautiful and elaborate contrivance by which all the infinitely numerous pollen granules are swept out of the conjoined anthers of each flower, before the stigma of that individual flower is ready to receive them. And as this flower is never visited, at least in my garden, by insects, it never gets a seed, though by placing pollen from one flower on the stigma of another, I raise plenty of seedlings. Another species of Lobelia, which is visited by bees, seeds freely in my garden. In very many other cases, though there is no special mechanical contrivance to prevent the stigma receiving pollen from the same flower, yet, as Sprengel and more recently Hildebrand and others have shown, and as I can confirm, either the anthers burst before the stigma is ready for fertilization, or the stigma is ready before the pollen of that flower is ready, so that these so-named dichogamous plants have in fact separated sexes, and must habitually be crossed. So it is with the reciprocally dimorphic and trimorphic plants previously alluded to. How strange are these facts! How strange that the pollen and stigmatic surface of the same flower, though placed so close together, as if for the very purpose of self-fertilization, should be in so many cases mutually useless to each other. How simply are these facts explained on the view of an occasional cross with a distinct individual being advantageous or indispensable. If several varieties of the cabbage, radish, onion, and of some other plants be allowed to seed near each other, a large majority of the seedlings thus raised turn out, as I found, mongrels. For instance, I raised 233 seedling cabbages from some plants of different varieties growing near each other, and of these only 78 were true to their kind, and some even of these were not perfectly true. Yet the pistil of each cabbage flower is surrounded not only by its own 6 stamens, but by those of the many other flowers on the same plant, and the pollen of each flower readily gets on its stigma without insect agency, for I have found that plants carefully protected from insects produce the full number of pods. How then comes it that such a vast number of the seedlings are mongrelized? It must arise from the pollen of a distinct variety having a prepotent effect over the flower's own pollen, and that this is part of the general law of good being derived from the intercrossing of distinct individuals of the same species. When distinct species are crossed, the case is reversed, for a plant's own pollen is always prepotent over foreign pollen. But to this subject we shall return in a future chapter. In the case of a large tree covered with innumerable flowers, it may be objected that pollen could seldom be carried from tree to tree, and at most only from flower to flower on the same tree. And flowers on the same tree can be considered as distinct individuals only in a limited sense. I believe this objection to be valid, but that nature has largely provided against it by giving to trees a strong tendency to bear flowers with separated sexes. When the sexes are separated, although the male and female flowers may be produced on the same tree, pollen must be regularly carried from flower to flower, and this will give a better chance of pollen being occasionally carried from tree to tree. That trees belonging to all orders have their sexes more often separated than other plants, I find to be the case in this country, and at my request Dr. Hooker tabulated the trees of New Zealand, and Dr. Asa Gray those of the United States, and the result was as I anticipated. On the other hand, Dr. Hooker informs me that the rule does not hold good in Australia. But if most of the Australian trees are dichogamous, the same result will follow as if they bore flowers with separated sexes. I have made these few remarks on trees simply to call attention to the subject. Turning for a brief space to animals, various terrestrial species are hermaphrodites, such as the land mollusca and earthworms, but these all pair. As yet I have not found a single terrestrial animal which can fertilize itself. This remarkable fact, which offers so strong a contrast with terrestrial plants, is intelligible on the view of an occasional cross being indispensable. For owing to the nature of the fertilizing element, There are no means, analogous to the action of insects and of the wind with plants, by which an occasional cross could be effected with terrestrial animals without the concurrence of two individuals. Of aquatic animals there are many self-fertilizing hermaphrodites, but here the currents of water offer an obvious means for an occasional cross. As in the case of flowers, I have as yet failed, after consultation with one of the highest authorities, namely Professor Huxley, to discover a single hermaphrodite animal with the organs of reproduction so perfectly enclosed that access from without and the occasional influence of a distinct individual can be shown to be physically impossible. Cirripedes long appeared to me to present, under this point of view, a case of great difficulty, but I have been enabled, by a fortunate chance, to prove that two individuals, though both are self-fertilizing hermaphrodites, do sometimes cross. It must have struck most naturalists as a strange anomaly that, both with animals and plants, some species of the same family, and even of the same genus, though agreeing closely with each other in their whole organisation, are hermaphrodites, and some unisexual. But if, in fact, all hermaphrodites do occasionally intercross, the difference between them and unisexual species is, as far as function is concerned, very small. From these several considerations, and from the many special facts which I have collected, but which I am unable here to give, it appears that with animals and plants an occasional intercross between distinct individuals is a very general, if not universal, law of nature. Circumstances favourable for the production of new forms through natural selection. This is an extremely intricate subject. A great amount of variability, under which term individual differences are always included, will evidently be favourable. A large number of individuals, by giving a better chance within any given period for the appearance of profitable variations, will compensate for a lesser amount of variability in each individual, and is, I believe, a highly important element of success. Though nature grants long periods of time for the work of natural selection, she does not grant an indefinite period. For as all organic beings are striving to seize on each place in the economy of nature, if any one species does not become modified and improved in a corresponding degree with its competitors, it will be exterminated. Unless favourable variations be inherited by some at least of the offspring, nothing can be effected by natural selection. The tendency to reversion may often check or prevent the work, but as this tendency has not prevented man from forming by selection numerous domestic races, why should it prevail against natural selection? In the case of methodical selection, a breeder selects for some definite object, and if the individuals be allowed freely to intercross, his work will completely fail. But when many men, without intending to alter the breed, have a nearly common standard of perfection, and all try to procure and breed from the best animals, improvement surely but slowly follows from this unconscious process of selection, notwithstanding that there is no separation of selected individuals. Thus it will be under nature. For within a confined area, with some place in the natural polity not perfectly occupied, all the individuals varying in the right direction, though in different degrees, will tend to be preserved. But if the area be large, its several districts will almost certainly present different conditions of life, and then, if the same species undergoes modification in different districts, the newly formed varieties will intercross on the confines of each. But we shall see in the 6th chapter that intermediate varieties, inhabiting intermediate districts, will in the long run generally be supplanted by one of the adjoining varieties. Intercrossing will chiefly affect those animals which unite for each birth and wander much, and which do not breed at a very quick rate. Hence with animals of this nature, for instance birds, varieties will generally be confined to separate countries, and this I find to be the case. With hermaphrodite organisms which cross only occasionally, and likewise with animals which unite for each birth but which wander little and can increase at a rapid rate, a new and improved variety might be quickly formed on any one spot, and might there maintain itself in a body and afterward spread, so that the individuals of the new variety would chiefly cross together. On this principle, nurserymen always prefer saving seed from a large body of plants, as the chance of intercrossing is thus lessened. Even with animals which unite for each birth, and which do not propagate rapidly, we must not assume that free intercrossing would always eliminate the effects of natural selection, for I can bring forward a considerable body of facts showing that within the same area two varieties of the same animal may long remain distinct, from haunting different stations, from breeding at slightly different seasons, or from the individuals of each variety preferring to pair together. Intercrossing plays a very important part in nature by keeping the individuals of the same species or of the same variety true and uniform in character. It will obviously thus act far more efficiently with those animals which unite for each birth, but, as already stated, we have reason to believe that occasional intercrosses take place with all animals and plants. Even if these take place only at long intervals of time, the young thus produced will gain so much in vigour and fertility over the offspring from long continued self-fertilisation that they will have a much better chance of surviving and propagating their kind, and thus in the long run the influence of crosses, even at rare intervals, will be great. With respect to organic beings extremely low in the scale, which do not propagate sexually, nor conjugate, and which cannot possibly intercross, uniformity of character can be retained by them under the same conditions of life only through the principle of inheritance, and through natural selection, which will destroy any individuals departing from the proper type. If the conditions of life change, and the form undergoes modification, uniformity of character can be given to the modified offspring solely by natural selection preserving similar favourable variations. Isolation also is an important element in the modification of species through natural selection. In a confined or isolated area, if not very large, the organic and inorganic conditions of life will generally be almost uniform, so that natural selection will tend to modify all the varying individuals of the same species in the same manner. Intercrossing with the inhabitants of the surrounding districts will also be thus prevented. Moritz Wagner has lately published an interesting essay on this subject, and has shown that the service rendered by isolation in preventing crosses between newly formed varieties is probably greater even than I supposed. But from reasons already assigned, I can by no means agree with this naturalist that migration and isolation are necessary elements for the formation of new species. The importance of isolation is likewise great in preventing, after any physical change in the conditions, such as of climate, elevation of the land, etc., the immigration of better adapted organisms, and thus new places in the natural economy of the district will be left open to be filled up by the modification of the old inhabitants. Lastly, isolation will give time for a new variety to be improved at a slow rate, and this may sometimes be of much importance. If, however, an isolated area be very small, either from being surrounded by barriers, or from having very peculiar physical conditions, the total number of the inhabitants will be small, and this will retard the production of new species through natural selection by decreasing the chances of favourable variations arising. The mere lapse of time by itself does nothing either for or against natural selection. I state this because it has been erroneously asserted that the element of time has been assumed by me to play an all-important part in modifying species, as if all the forms of life were necessarily undergoing change through some innate law. Lapse of time is only so far important, and its importance in this respect is great, that it gives a better chance of beneficial variations arising and of their being selected, accumulated and fixed. It likewise tends to increase the direct action of the physical conditions of life in relation to the constitution of each organism. If we turn to nature to test the truth of these remarks, and look at any small isolated area, such as an oceanic island, although the number of the species inhabiting it is small, as we shall see in our chapter on geographic distribution, yet of these species a very large proportion are endemic, that is, have been produced there and nowhere else in the world. Hence an oceanic island at first sight seems to have been highly favourable for the production of new species. But we may thus deceive ourselves, for to ascertain whether a small isolated area or a large open area like a continent has been most favourable for the production of new organic forms, we ought to take the comparison within equal times, and this we are incapable of doing. Although isolation is of great importance in the production of new species, on the whole I am inclined to believe that largeness of area is still more important, especially for the production of species which shall prove capable of enduring for a long period and of spreading widely. Throughout a great and open area, not only will there be a better chance of favourable variations arising from the large number of individuals of the same species there supported, but the conditions of life are much more complex from the large number of already existing species, and if some of these many species become modified and improved, others will have to be improved in a corresponding degree, or they will be exterminated. Each new form also, as soon as it has been much improved, will be able to spread over the open and continuous area, and will thus come into competition with many other forms. Moreover, great areas, though now continuous, will often, owing to former oscillations of level, have existed in a broken condition, so that the good effects of isolation will generally, to a certain extent, have concurred. Finally, I conclude that, although small isolated areas have been in some respects highly favourable for the production of new species, yet that the course of modification will generally have been more rapid in large areas, and what is more important, that the new forms produced on large areas, which already have been victorious over many competitors, will be those that will spread most widely and will give rise to the greatest number of new varieties and species. They will thus play a more important part in the changing history of the organic world. In accordance with this view, we can perhaps understand some facts which will be again alluded to in our chapter on geographical distribution. For instance, the fact of the productions of the smaller continent of Australia now yielding before those of the larger Europeo-Asiatic area. Thus also it is that continental productions have everywhere become so largely naturalized on islands. On a small island the race for life will have been less severe, and there will have been less modification and less extermination. Hence we can understand how it is that the flora of Madeira, according to Oswald Heer, resembles to a certain extent the extinct tertiary flora of Europe. All freshwater basins taken together make a small area compared with that of the sea or of the land. Consequently, the competition between freshwater productions will have been less severe than elsewhere. New forms will have been more slowly produced, and old forms more slowly exterminated. And it is in freshwater basins that we find 7 genera of gonoid fishes, remnants of a once preponderant order. And in freshwater we find some of the most anomalous forms now known in the world, as the Ornithorhynchus and Lepidosiren, which, like fossils, connect to a certain extent orders at present widely separated in the natural scale. These anomalous forms may be called living fossils. They have endured to the present day from having inhabited a confined area, and from having been exposed to less varied and therefore less severe competition. To sum up, as far as the extreme intricacy of the subject permits, the circumstances favourable and unfavourable for the production of new species through natural selection, I conclude that for terrestrial productions, a large continental area which has undergone many oscillations of level will have been the most favourable for the production of many new forms of life, fitted to endure for a long time and to spread widely. While the area existed as a continent, the inhabitants will have been numerous in individuals and kinds, and will have been subjected to severe competition. When converted by subsistence into large separate islands, there will still have existed many individuals of the same species on each island. Intercrossing on the confines of the range of each new species will have been checked. After physical changes of any kind, immigration will have been prevented, so that new places in the polity of each island will have had to be filled up by the modification of the old inhabitants, and time will have been allowed for the varieties in each to become well modified and perfected. When, by renewed elevation, the islands were reconverted into a continental area, there will again have been very severe competition. The most favoured or improved varieties will have been enabled to spread. There will have been much extinction of the less improved forms, and the relative proportional numbers of the various inhabitants of the reunited continent will again have been changed, and again there will have been a fair field for natural selection to improve still further the inhabitants, and thus to produce new species. That natural selection generally acts with extreme slowness, I fully admit. It can only act when there are places in the natural polity of a district which can be better occupied by the modification of some of its existing inhabitants. The occurrence of such places will often depend on physical changes, which generally take place very slowly, and on the immigration of better adapted forms being prevented. As some few of the old inhabitants become modified, the mutual relations of others will often be disturbed, and this will create new places ready to be filled up by better adapted forms. But all this will take place very slowly. Although all the individuals of the same species differ in some slight degree from each other, it would often be long before differences of the right nature in various parts of the organization might occur. The result would often be greatly retarded by free intercrossing. Many will exclaim that these several causes are amply sufficient to neutralize the power of natural selection. I do not believe so, but I do believe that natural selection will generally act very slowly, only at long intervals of time, and only on a few of the inhabitants of the same region. I further believe that these slow intermittent results accord well with what geology tells us of the rate and manner at which the inhabitants of the world have changed. Slow though the process of selection may be, if feeble man can do much by artificial selection, I can see no limit to the amount of change, to the beauty and complexity of the co-adaptations between all organic beings, one with another, and with their physical conditions of life, which may have been effected in the long course of time through nature's power of selection, that is, by the survival of the fittest. Extinction caused by natural selection. This subject will be more fully discussed in our chapter on geology, but it must here be alluded to, from being intimately connected with natural selection. Natural selection acts solely through the preservation of variations in some way advantageous, which consequently endure. Owing to the high geometrical rate of increase of all organic beings, each area is already fully stocked with inhabitants, and it follows from this that as the favoured forms increase in number, so generally will the less favoured decrease and become rare. Rarity, as geology tells us, is the precursor to extinction. We can see that any form which is represented by few individuals will run a good chance of utter extinction during great fluctuations in the nature or the seasons, or from a temporary increase in the number of its enemies. But we may go further than this, for as new forms are produced, unless we admit that specific forms can go on indefinitely increasing in number, many old forms must become extinct. That the number of specific forms has not indefinitely increased, geology plainly tells us, and we shall presently attempt to show why it is that the number of species throughout the world has not become immeasurably great. We have seen that the species which are most numerous in individuals have the best chance of producing favourable variations within any given period. We have evidence of this in the fact stated in the second chapter, showing that it is the common and diffused or dominant species which offer the greatest number of recorded varieties. Hence, rare species will be less quickly modified or improved within any given period. they will consequently be beaten in the race for life by the modified and improved descendants of the commoner species. From these several considerations, I think it inevitably follows that as new species in the course of time are formed through natural selection, others will become rarer and finally extinct. The forms which stand in closest competition with those undergoing modification and improvement will naturally suffer most. And we have seen in the chapter on the struggle for existence that it is the most closely allied forms, varieties of the same species, and species of the same genus or related genera, which, from having nearly the same structure, constitution, and habits, generally come into the severest competition with each other. Consequently, each new variety or species, during the progress of its formation, will generally press hardest on its nearest kindred and tend to exterminate them. We see the same process of extermination among our domesticated productions, through the selection of improved forms by man. Many curious instances could be given showing how quickly new breeds of cattle, sheep, and other animals, and varieties of flowers, take the place of older and inferior kinds. In Yorkshire it is historically known that the ancient black cattle were displaced by the longhorns, and that these were swept away by the shorthorns, I quote the words of an agricultural writer, as if by some murderous pestilence. Divergence of character. The principle which I have designated by this term is of high importance, and explains, as I believe, several important facts. In the first place, varieties, even strongly marked ones, though having somewhat of the character of species, as is shown by the hopeless doubts in many cases how to rank them, yet certainly differ far less from each other than do good and distinct species. Nevertheless, according to my view, varieties are species in the process of formation, and are, as I have called them, incipient species. How then does the lesser difference between varieties become augmented into the greater difference between species? That this does habitually happen, we must infer from most of the innumerable species throughout nature presenting well-marked differences, whereas varieties, the supposed prototypes and parents of future well-marked species, present slight and ill-defined differences. Mere chance, as we may call it, might cause one variety to differ in some character from its parents, and the offspring of this variety again to differ from its parent in the very same character and in a greater degree. But this alone would never account for so habitual and large a degree of difference as that between the species of the same genus. As has always been my practice, I have sought light on this head from our domestic productions. We shall here find something analogous. It will be admitted that the production of races so different as Shorthorn and Hereford cattle, race and cart horses, the several breeds of pigeons, etc., could never have been effected by the mere chance accumulation of similar variations during many successive generations. In practice, a fancier is, for instance, struck by a pigeon having a slightly shorter beak. Another fancier is struck by a pigeon having a rather longer beak, and on the acknowledged principle that fanciers do not and will not admire a medium standard, but like extremes, they both go on, as has actually occurred with the subbreeds of the tumbler pigeon, choosing and breeding from birds with longer and longer beaks, or with shorter and shorter beaks. Again, we may suppose that at an early period of history, the men of one nation or district required swifter horses, while those of another required stronger and bulkier horses. The early differences would be very slight, but in the course of time, from the continued selection of swifter horses in the one case and of stronger ones in the other, the differences would become greater and would be noted as forming two sub-breeds. Ultimately, after the lapse of centuries, these sub-breeds would become converted into two well-established and distinct breeds. As the differences became greater, the inferior animals with intermediate characters, being neither very swift nor very strong, would not have been used for breeding, and will thus have tended to disappear. Here then we see in man's productions the action of what may be called the principle of divergence, causing differences, at first barely appreciable, steadily to increase, and the breeds to diverge in character, both from each other and from their common parent. But how, it may be asked, can any analogous principle apply in nature? I believe it can and does apply most efficiently, though it was a long time before I saw how, from the simple circumstance that the more diversified the descendants from any one species become in structure, constitution and habits, by so much will they be better enabled to seize on many and widely diversified places in the polity of nature, and so be enabled to increase in numbers. We can clearly discern this in the case of animals with simple habits. Take the case of a carnivorous quadruped, of which the number that can be supported in any country has long ago arrived at its full average. If its natural power of increase be allowed to act, it can succeed in increasing, the country not undergoing any change in conditions, only by its varying descendants seizing on places at present occupied by other animals, some of them, for instance, being enabled to feed on new kinds of prey, either dead or alive, some inhabiting new stations, climbing trees, frequenting water, and some perhaps becoming less carnivorous. The more diversified in habits and structure the descendants of our carnivorous animals become, the more places they will be enabled to occupy. What applies to one animal will apply throughout all time to all animals, that is, if they vary, for otherwise natural selection can effect nothing. So it will be with plants. It has been experimentally proved that if a plot of ground be sown with one species of grass, and a similar plot be sown with several distinct genera of grasses, a greater number of plants and a greater weight of dry herbage can be raised in the latter than in the former case. The same has been found to hold good when one variety and several mixed varieties of wheat have been sown on equal spaces of ground. Hence, if any one species of grass were to go on varying, and the varieties were continually selected which differed from each other in the same manner, though in a very slight degree, as do the distinct species and genera of grasses, a greater number of individual plants of this species, including its modified descendants, would succeed in living on the same piece of ground. and we know that each species and each variety of grass is annually sowing almost countless seeds, and is thus striving, as it may be said, to the utmost to increase in number. Consequently, in the course of many thousand generations, the most distinct varieties of any one species of grass would have the best chance of succeeding and of increasing in numbers, and thus of supplanting the less distinct varieties. And varieties, when rendered very distinct from each other, take the rank of species. The truth of the principle that the greatest amount of life can be supported by great diversification of structure is seen under many natural circumstances. In an extremely small area, especially if freely open to immigration, and where the contest between individual and individual must be very severe, we always find great diversity in its inhabitants. For instance, I found that a piece of turf, 3 feet by 4 in size, which had been exposed for many years to exactly the same conditions, supported 20 species of plants, and these belonged to 18 genera and to 8 orders, which shows how much these plants differed from each other. So it is with the plants and insects on small and uniform islets, also in small ponds of fresh water. Farmers find that they can raise more food by a rotation of plants belonging to the most different orders. Nature follows what may be called a simultaneous rotation. Most of the animals and plants which live close around any small piece of ground could live on it, supposing its nature not to be in any way peculiar, and may be said to be striving to the utmost to live there. But it is seen that where they come into closest competition, the advantages of diversification of structure, with the accompanying differences of habit and constitution, determine that the inhabitants, which thus jostle each other most closely, shall, as a general rule, belong to what we call different genera and orders. The same principle is seen in the naturalization of plants through man's agency in foreign lands. It might have been expected that the plants which would succeed in becoming naturalized in any land would generally have been closely allied to the indigenes, for these are commonly looked at as especially created and adapted for their own country. It might also perhaps have been expected that naturalized plants would have belonged to a few groups more especially adapted to certain stations in their own homes. But the case is very different. And Alphonse de Candolle has well remarked, in his great and admirable work, that floras gain by naturalization proportionally with the number of the native genera and species, far more in new genera than in new species. To give a single instance, in the last edition of Dr. Asa Gray's Manual of the Flora of the Northern United States, 260 naturalized plants are enumerated, and these belong to 162 genera. We thus see that these naturalized plants are of a highly diversified nature. They differ, moreover, to a large extent from the indigenes, for out of the 162 naturalized genera, no less than 100 genera are not there indigenous, and thus a large proportional addition is made to the genera now living in the United States. By considering the nature of the plants or animals which have in any country struggled successfully with the indigenes, and have there become naturalized, we may gain some crude idea in what manner some of the natives would have had to be modified in order to gain an advantage over their compatriots, and we may at least infer that diversification of structure amounting to new generic differences would be profitable to them. The advantage of diversification of structure in the inhabitants of the same region is, in fact, the same as that of the physiological division of labour in the organs of the same individual body, a subject so well elucidated by Milne Edwards. No physiologist doubts that a stomach, by being adapted to digest vegetable matter alone, or flesh alone, draws most nutriment from these substances. So in the general economy of any land, the more widely and perfectly the animals and plants are diversified for different habits of life, so will a greater number of individuals be capable of there supporting themselves. A set of animals, with their organisation but little diversified, could hardly compete with a set more perfectly diversified in structure. It may be doubted, for instance, whether the Australian marsupials, which are divided into groups differing but little from each other, and feebly representing, as Mr. Waterhouse and others have remarked, our carnivorous, ruminant and rodent mammals, could successfully compete with these well-developed orders. In the Australian animals we see the process of diversification in an early and incomplete stage of development. End of section 2 of chapter 4.